Imagine a world where human strength is no longer limited by biology. A world where a construction worker can lift hundreds of kilograms as if it were nothing more than a lightweight object. A world where soldiers can carry heavy equipment for hours without collapsing from exhaustion. A world where rescue workers can move massive pieces of rubble with ease, saving lives trapped beneath collapsed buildings. And all of this does not happen because humans have evolved, but because humans have learned how to enhance themselves with machines. Machines that do not replace the human body, but work with it. Machines that wrap around the human frame like a second skeleton. This is the world of exoskeleton technology. And although it sounds like something from science fiction, it is already becoming reality today. But to understand how revolutionary this is, we need to start from something simple. What actually limits human strength? The answer lies in biology. The human body is incredibly efficient, but not designed for extreme load-bearing performance. Muscles fatigue. Bones have structural limits. Joints wear down under pressure, and the nervous system slows when energy is depleted. In everyday life, we don't notice these limits. We walk. We carry groceries. We lift small objects. Everything feels normal. But in industries like construction, logistics, military operations, and disaster response, these limits become very real. A worker lifting heavy materials repeatedly becomes exhausted. A soldier carrying full combat gear becomes slower over time. A rescue worker lifting debris risks serious injury. And this is where humanity began searching for a solution, not to replace the human body, but to enhance it. And that is how the idea of exoskeletons was born. At its core, an exoskeleton is a wearable mechanical structure placed outside the human body. If bones form the internal skeleton, the exoskeleton acts as an external support system, a mechanical framework that moves with the human body, not independently, not automatically like a robot, but in synchronization with human motion. A partnership between biology and engineering.
Imagine wearing a suit, but this suit is made of metal, motors, sensors, and artificial intelligence systems. Every time you move your arm, bend your back, or lift your legs, the suit assists you. It amplifies your strength. It reduces strain. It distributes weight. But how does a machine understand human intention? The answer lies in sensors. Modern exoskeletons are equipped with highly advanced sensor systems. Pressure sensors detect force applied by the body. Motion sensors track joint angles. Acceleration sensors measure movement speed. And most importantly, electromyography sensors, or EMG sensors, detect electrical signals generated by muscles before movement happens. This means the exoskeleton doesn't just react to movement, it anticipates it. When your brain sends a signal to lift your arm, your muscles generate a tiny electrical impulse. The exoskeleton detects this impulse instantly. Within milliseconds, its motors activate. Assistance is applied exactly where needed. The result is a movement that feels natural, but significantly easier.
It does not remove the weight. It redistributes it between human and machine. Now, let's break down what is actually happening mechanically. An exoskeleton system typically consists of several core components: a structural frame that supports the body, electric motors that generate movement assistance, hydraulic or pneumatic systems for high-force support, a battery pack that powers the system, and a central control unit that acts as the brain. All of these must work in perfect synchronization. If one system is delayed, the movement feels unnatural. If calibration is off, balance can be affected. Precision is critical. Now imagine a real-world scenario. A worker on a construction site. Normally, lifting heavy materials repeatedly would cause fatigue and strain on the lower back. But with an exoskeleton, the load is partially transferred to the mechanical frame.
The worker bends down, lifts a heavy object, and instead of relying entirely on muscle strength, the exoskeleton supports the motion.
The weight feels reduced. The strain on the spine decreases. The body remains stable, and fatigue is significantly delayed. This has enormous implications for workplace safety. Many injuries in construction come from repetitive strain. Exoskeletons aim to reduce exactly that. But construction is just one application. In the military field, exoskeletons are being tested to enhance soldier endurance. A soldier in combat often carries equipment weighing 30 to 50 kilograms or more. Weapons, ammunition, communication systems, medical supplies. All of this must be carried across difficult terrain, over long distances, for extended periods. Exoskeletons help distribute this weight across the mechanical structure of the suit. This reduces strain on muscles, improves endurance, and allows soldiers to maintain performance for longer durations. But beyond strength, stability also matters, because in extreme conditions, fatigue can become life-threatening. In the medical field, exoskeletons serve an entirely different purpose.
Rehabilitation. Patients with spinal injuries or mobility disorders can use exoskeleton systems to walk again. Sensors detect weak muscle signals or neural intent, and the exoskeleton assists in controlled movement, step by step. Over time, this repeated motion helps retrain the nervous system. In some cases, patients regain partial natural movement, as if the body is relearning how to function. This is one of the most hopeful applications of the technology, a bridge between paralysis and mobility, between limitation and recovery. But despite all this promise, exoskeleton technology still faces significant challenges. One of the biggest is energy. High-force motors require large amounts of power, yet the system must remain lightweight enough to be wearable. Battery technology is still catching up. Another challenge is comfort. Human bodies are complex and varied. A system that works for one person may not fit another. Too rigid and it restricts movement. Too loose and it loses effectiveness.
Ergonomic design is extremely difficult. Then there is cost. Advanced exoskeleton systems are still expensive, making widespread adoption difficult in many industries. But progress is happening rapidly. Every year, exoskeletons become lighter, stronger, smarter, more responsive. Now, let's step back and look at the bigger question. If humans can be mechanically enhanced, what does human strength even mean anymore? Is strength still purely biological, or has it become a combination of human and machine? Imagine the future. Construction workers lifting materials effortlessly. Emergency responders clearing disaster zones in record time. Elderly individuals regaining mobility with lightweight wearable systems. Industrial workers performing physically demanding tasks without injury. A world where physical limitations are no longer absolute. But this also introduces ethical questions. If a worker uses an exoskeleton to perform more work, is it empowerment or exploitation? If machines enhance human strength, does that create inequality between enhanced and non-enhanced humans? And if exoskeletons become extremely advanced in the future, will humans still define their own physical limits? Or will technology define them for us? Like every major technological revolution in history, exoskeletons are not just about machines. They are about humanity, about how we redefine ability, about how we extend the limits of the human body, and about how we choose to integrate technology into our physical existence. Because in the end, exoskeletons do not replace humans. They amplify them. They take what already exists and push it further. And perhaps one day, when someone lifts a massive object effortlessly, we will no longer see it as superhuman strength, but as something natural,
a collaboration between muscle and machine, between biology and engineering, between human intention and mechanical precision. And that is when we realize the future of human strength has already begun.